Hey everybody, what I'm teaching in class, well actually I started last week, is shear and moment diagrams. So I thought we would cover one of those examples today in case that's where you happen to be in your solid mechanics class. So maybe it'll be helpful. Okay, now we're going to start out with a simple one. All right, so this is what this one looks like. We've got a pin at A, we've got a roller at B, we've got this beam, and then we've got the triangular shape distributed load. Now, for this problem, it wants us to find the equations for the shear force V and the bending moment M at any location along the beam. Origin's going to be at A over here. And then after we get those equations, we're going to use those to draw the shear and moment diagrams. All right, now this problem is from the Philpot book, just so everybody knows what book we got it out of. So first thing we need to do is we need to figure out what's going on with the external supports, right? So I have this pin, I've got this roller here. I need to figure out what's going on there because that's going to change what happens internally to my beam, right? So that's going to be step one, okay, is get the external forces. So let's do that first. And to do that, we're just going to do a regular free body diagram, just like we always do. We're going to label our forces. All right, so a pin, we've got AY. Technically, we should draw AX, but AX is going to be 0 because there's no other X components here. We've got a roller at B, so it's going to be a Y component. And then we've got this distributed load. So for the triangular shape one, we're basically going to use what I always say is like the area equation for a triangle. So we're going to have 1/2 times the intensity times the length. Okay, so that's going to be 1/2 W0L. And then we need to know where to place it on the beam. Notice I didn't put it in the middle. And that's because since this is triangular, we need to have the resultant force acting through the centroid of the triangular region. So if y'all remember, centroid of a triangle is basically 1/3 of the length from this bigger side over here. Right, so that's where we're going to be. So this will be L/3, just from the location of a centroid of a triangle. All right, so now that we've got this established, we can go ahead and solve for AY and BY. And I think I'm going to go ahead and start with a moment about B for my equilibrium equation. All right, counterclockwise will be positive. So AY is going to create a moment. If we look, that's going to go clockwise, so it's a negative moment. And then that distance, it's not written up here, but the total distance from A to B is L, so this would be 2L/3. So this length here would be L. All right, so we got that, and then I have this force here. So now that one's pushing down, right? So that's going to be counterclockwise, so positive. So positive 1/2 W0L, and then that distance is L/3. And then that's it, set it equal to 0, because we're doing the moment about B. So now that we have this, I can go ahead and solve for AY. And that is going to equal 1/6 omega naught L. All right. So basically move this over, it becomes negative, so the negatives cancel. This L will cancel one of these. Then we have the 2 times the 3, which gives us the 6 here. Okay, so now we know what's going on at AY. Now let's look at the sum of the forces in the Y direction so we can get BY. All right, so AY is this equation here, so let's just put that in our expression. Then we have the minus 1/2 W0L plus BY. Set that equal to 0. All right, so from that you can get BY. So, put these together. Common denominator here will be 6, right? So that'll be -3/6. So 1/6 minus 3/6 is minus 2/6, which is 1/3. When you move it over, it becomes positive. So we have positive 1/3 W0L for BY. So now we know what's going on at AY and BY. Now we're ready to get to the shear and moment part. Okay, so what we need to do is draw a section. In this problem, we only have one distributed load up here. Our supports are on the ends, so we only need one section. All right, so just draw the line there. Remember, the origin's going to be at A. So basically that means we're going to have a distance x that goes from A over to that line that we just drew. Okay. So now let's draw the free body diagram for this left side, and let's see what we should put on there. All right, so you can see where I cut it. I always put a point C here where it's been cut. Now I need all the forces to the left of that line, so that means I need AY. So that's the 1/6 W0 L, and I have this distributed load up here, right? Now let's look at that though. So this distributed load, it starts at 0 just like it did, before for the whole beam. But this time it's only going up to this point right here, right? It's not going all the way up to W0. W0 was over here at B. I obviously am not at W0 right here because I haven't gone all the way to B. Okay, so I need to find a new expression for that. And the easiest thing to do for that is basically use like a similar triangle type thing. So let's look at that. So if this is X, I want to figure out what that length is, or not length, that intensity. And then if I look at the original distributed load, this is L, and this is W0. All right, so if we do similar triangles here, I can say the question mark over X needs to equal W0 over L, right? And then I want to find that question mark. So question mark would be W0 X over L. So that is what we are looking at for our distributed load here. So basically, if I were to look at the distributed load now, it's going to look something like this. Okay, so before we had the W0, but we went all the way over. Now we're not going all the way over, we're just going over this distance X. So this is now the new distributed load. Okay, so then when I put it on this diagram here, we're still going to use the 1/2 times the intensity, right, which is now W0 XL over L, and then we need the length here, which is X, right? So we're going to multiply by X. So this is 1/2 W0 X squared over L, right? And this is something that a lot of people will forget to do. They just automatically use this W0, but that's not right, because we're not going all the way to that max value. We're going to this smaller value, right? So we have to recalculate it. And like I said, the similar triangles typically is the easiest way to do that. Okay, so we got that. Now we need our location. Remember, this is still going to act through the centroid. So now it's going to be X over 3 for that location. All right. Now, those are the external forces. Now let's look internally. I got V. Sign convention we want to use is going down here. And then M will be counterclockwise. And I chose those directions because the sign convention typically states you want your shear to make your section rotate clockwise. So obviously if I've got this section here, if I push down, it's going to rotate clockwise. And then for your moment, you want to draw the moment in the direction that's going to cause compression in the top surface of your beam. All right, so I want the moment to go counterclockwise because that would give us compression up here. So this is going to be what you're going to have anytime you have this left-hand section. Right, if you use the right-hand section, these would be reversed. Okay, but I always use the left-hand section just because I think it's easier. Okay, so that will be our diagram right there. So now we want to get v and m, right? We want equations of those as functions of x. So let's go ahead, we're going to do just regular equilibrium equations again. Okay, so forces in the y direction, up will be positive. So I've got 1/6 W naught L, and then we have the distributed load, right? So that's going to be minus 1/2 W naught X squared over L, and then we have minus V. Set it to 0. All right, so now I want to solve for V. So easiest thing is basically move this over. So V is going to be 1/6 W naught minus the 1/2 W naught X squared over L. Okay, and then this is our function for V. So basically with this equation, I can plug in any value for X, and then I will find the shear force at that point. So let's say I want an X of 1. Right, I want to know what the shear is at that length of 1, right? I just plug in x equals 1 here, and that would give me my shear. Okay, now we need to do the same thing for m. So for m, obviously it's a moment, so let's do a moment equation, and we're going to take it about this point C. Okay, counterclockwise will be positive. All right, so for this one, that's going to be a negative because it goes clockwise. So you got negative 1/6 W naught L. Distance here is x. So multiply by x. And then we've got this force here. All right, now this one pushing down, right? So it's going to be positive. So the force is the 1/2 W naught X squared over L. Distance is going to be x over 3. Right, and then finally we have plus m. It's plus because it's counterclockwise. Okay, so to 0. Now I need to solve for m. So basically we can move these terms over. Okay, so m is going to be 1/6 W naught L X, and then minus, what is this, 1/6 W naught X cubed over L. All right, and then that's what we get for that one. And now this will allow us to find our bending moment, our internal bending moment at any location X, right? So you could plug in a value for X, get M. Now what we're going to do is we're going to use these to get our shear moment diagrams. All right, so let's make our diagrams. Now, when you do your diagrams, first thing you want to do is you want to draw like the original system that you had with all of the external forces shown. All right, so I want to label AY and BY. All right, so there's AY, and then we got BY over here. And then we want to put our distance. So this is L. This looks like an arrow, but that's the L. And then up top, we want to draw the actual distributed load. All right, and we want to do that for when we learn how to do the graphical method of drawing these. Because when we use the graphical method, we can look at the shape and kind of figure out what's going on. All right, we'll save that one for another video later on though. Okay, so this is what we're going to have first, right? Just repeat of the problem. And then below that, we're going to have the shear diagram. So this will be X, this will be V. Usually you put your units on here. We don't really have units in this problem. And what we want to do now is we have this equation. So you want to put your boundaries for X. Okay, so for this equation is valid for X values going from 0 to L. Okay, so at X equals 0, what's V going to be? Well, we plug in 0 for X, right? So basically the second term here goes away. So that's going to go away. So we end up with V equals 1/6 W naught L. Okay, so that's our starting point. Let's go ahead and find it when X is L. All right, so when it's L, we're going to have the 1/6 W naught L minus 1/2 W naught L squared over L. Notice those cancel. All right, so then that ends up being what? We need a common denominator, right? So this will be 1/6 minus 3/6. So that's minus 2/6, which is minus 1/3 W naught L. Okay, so these are going to be our endpoints, basically. Okay, so this one's positive, so let's just say it's right here. Okay, and then this one is negative down here. So let's put this over here. And then we need to connect these lines. Now, to do that, you need to look at the form of the equation, because it might be linear, it might be quadratic, you know, it might be a constant, whatever case is. So here, this is quadratic, right? Because 2 is the highest exponent. This is a negative, right? So it's going to be like, kind of like that shape. So we just need to connect these, just like that. All right. And then draw a line back up to the x-axis. And there you have it. Okay. Now notice we cross the x-axis right here. Right, so if I'm crossing the x-axis right here, what has to happen with v? Well, v is going to be 0, right? Because notice this is v. So if I'm at the x-axis, v has to be 0. So I need to know where this location is for when I do my moment diagram. So how do you think we could find that location? Well, I'm thinking we should take this equation, set v equal to 0, and then solve for x. I think that's what we should do. Okay, so let's do that. So let's say at v equals 0, we're going to have 0 equals 1/6 W naught L minus 1/2 W naught X squared over L. And then we need to solve for x. All right. So let's see, what would that be? I haven't worked this out yet. So we got that. Okay, so now we can multiply over here by the L. The W naughts, those are going to cancel. So let's get rid of that. And let me get my calculator out here. Okay, so what we end up with over here is basically the square root of 1/3 L squared. That's what x will be. All right, so if you use the calculator for that, you get 0.57735 L. Okay, so that is where we cross the x-axis, where v would be 0, right here. Okay. Okay, so that's where that happens. Now that we have that information, let's go ahead and last diagram here. See, aren't y'all glad I picked a shorter problem? Some of these get really long. Okay, so now for the moment, we're going to do the same thing. We've got this equation now for the moment. So this is valid for anywhere for x from 0 to L, right? So I want to do the same thing we did here. I want to look at the boundaries. So x is 0, so plug x in here, so 0 everywhere x is. So that means we're going to have basically 0, right? Because this first term goes away, and so does the second term. Oops. So that term goes away. So we start at 0, and then at x equals L, what are we going to get? We get 1/6 W naught L times L minus 1/6 W naught L cubed over L. Notice this cancels one of those. So now we have the L, both of these have L squared, right? So we have 1/6 W naught L squared minus 1/6 W naught L squared. So this is going to equal 0 also. Okay, well that made it easy, right? So put our value here and then here. And now look at the form of your line, right? So it's a cubic. So it's a cubic, and then the last thing here, where v equals 0, we're going to have our max moment for this equation, right? So let's just draw it up here. And basically it's going to look something like that. Right? It's a cubic, so it's hard to know exactly what it looks like unless you plot it out in MATLAB or something. But that looks close enough. Okay, so now we've got this, and I can find the value here, right? Because I know where this happens. It happens at this value of x. So I can take this for x, plug it in this equation here. All right. So where v equals 0, m then is going to be 1/6 W naught L times that 0.57735 L minus the 1/6 W naught 0.57735 L. You got to cube that, divide by L. All right, and then what you get from that, if you work all that out, I'm just going to go with what the book has here since I'm out of room here. But what you'll get is 0.06415 W naught L squared. Whoops, right there. Man, out of room, y'all. So let's write this up here. Okay, so then that's what we would get there. So that would be our max moment at this point where v crosses that x-axis, right? Because v is 0. And then, you know, make it nice, shade it there. All right, so those are the steps for that problem where we have just the one triangular shaped distributed load. All right, so again, get your equations, and then you want to look at the endpoints for your equations. A lot of the times you're going to have more than one section because you'll have supports in like the middle of the beam or whatever the case might be, or you might have two different uniform distributed loads, something like that. So you want to look at all your sections, you want to do the endpoints for each section, and then that'll help you construct your diagram. All right, but that's how you do it using equations as a function of x like we did here. Hopefully y'all found that helpful. Maybe next time we will do one of the graphical ones. It's a little bit shorter. All right. See y'all next time.